everyone. My name is Csilla Orgel and I'm working at ESA ESTEC in the science-based team together with James Carpenter. And today, actually, I'm going to talk about the need for future landing site studies and also a work we are doing at ESA in terms of landing sites. And also, I would like to advertise our Splinter meeting this afternoon. So, the exploration of the moon is the second cornerstone of the Terra Novae exploration program. So we would like to send the first European astronaut to the moon by 2030. And also we would like to have a regular and substantial access during the 30s. And also we would like to grow science, technology, and utilization and establish an international base and also to prepare for future human missions to Mars. So we already started to build up partnerships with international partners. So we are going to send 6 science and technology payloads to the lunar surface by 2026. And the first instrument will be the peregrine ion trap mass spectrometer. That will be ESA's first science on the moon, and it will be launched later this year. So you know that there are probably future opportunities. So, and we would like to be involved in the landing site selection process. So the question is then where do we want to go, and also which areas we could access. So typically landing site assessments are based on various criteria. So we have engineering constraints, and also we would like to fulfill our science goals. So terrain properties, landing precision, and operation constraints are playing the major role when we are targeting the South Polar area, especially slopes, Earth visibility, and solar illumination. And of course, the science potential in case of a South Polar mission, everybody is focusing on finding subsurface water ice, but of course there are other science questions we could address in various locations, like the impact cratering processes and bombardment history of or the young volcanism, etc. So before taking up my duty as an exploration scientist at ESA ESTEC, I was a research fellow from end of 2019 until end of 2022. And I worked on mainly on landing site assessment for future missions. And including working on a regional scale landing site assessment for future robotic exploration missions to the South Pole of the moon. And in that work, I was focusing on combining engineering constraints with science and finding locations which meet all those requirements. And I call those areas as compliant terrains. And this work is already submitted to the Planetary Science Journal. So you can get more information about that later this year. So in this regional scale landing site study, we used 120 meter per pixel baseline. So we used LoRa-derived GDR data products, slope, Earth visibility, and solar illumination. And because we were not tied to any missions, we used only the Mezzerico et al. 2011 average Earth visibility and solar illumination maps. And also the area of interest is within the white dash box. It's between the 80 south to the South Polar area. And then we used thermally derived water ice stability models, which are based on LRO diviner data. And we used the Page et al. 2010 model and the Warren et al. 2020 model. You see both maps on the screen. We regridded the data to 120 meter per pixel in order to align with the LoRa GDR data products. So what we did with these thermal models, apart from combining them, so we, in fact, we wanted to see which areas overlap in both of the models to have a higher confidence to find potential subsurface water ice areas. And then what we did, we combined the engineering constraints, slopes, Earth's visibility, solar illumination with the water ice stability models. And we created two scenarios, a least constraint scenario and a most constraint scenario. And for all these parameters, we set it a threshold value, you can see in this table. And all these parameters were chosen for a robotic exploration mission, which uses solar panels and also direct to Earth communications. So the outcome of that were the Boolean rasters. So raster data, which has only pixel values of 0s and 1. 1 means that all the constraints are met, and 0s were not all the constraints met. So on the left-hand side, you see the result of the spatial distribution of compliant terrains for the least constraint scenario, and altogether we found an area size of 1/3 of the Netherlands, which are compliant. And if we go for the most constrained scenario, we only found the area size of less than Malta, where we could potentially safely land and find subsurface volatiles. And we also investigated the minimum and maximum size of these compliant terrains. So on the left-hand side, you see an image subset of the Shackleton crater area and the compliant terrains with the blue. And on the right-hand side, you see the most constrained scenario. There are not many areas to see, but some of the bigger patches I highlighted with the cyan boxes. And how these compliant terrain look like, you see an example in the middle. So we call these connected contiguous areas. And the requirement was that the pixels are connected at least at one edge of the pixel. The largest connected area for the least constrained scenario was 430 square kilometers, while for the most constrained scenario, we received 5.6 square kilometers. And why we did this analysis is because we did actually perform a probability analysis of landing on these areas. And also we investigated geometric properties of these compliant terrains. But next, I'm gonna talk and advertise a landing site study, which was done by Sarah Bozeman et al. And she will be giving a talk tomorrow at 4 o'clock. And her work is based on this regional scale landing site assessment I was talking about. And finally, I would like to invite you to attend the Splinter meeting, which will be about the European view on the exploration of the moon. So we will be talking about landing sites, and I have 3 panelists, Sarah Bozeman, Caroline van der Bogert, and Jesse Flaho. And we have 1 hour from 2 to 3 to engage discussion on that topic. Thank you for your attention.